Want to start? Hi. Today we'll continue what we started in the previous lesson about conversions of units. And I'll give you some more examples on that to start with. And then we'll move on to errors and uncertainty. So the title is Conversions of Units. We are still in chapter 1, measurements. And we were talking about the metric system, SI unit metric system. And we said that we have metric systems or non-metric system. And we have to know how to convert from one system to another or within the same system. The example which we usually use is the density. It's a good example. Density is mass per volume, which means the unit usually we have for the mass is kilogram and the volume meter cube. So if I have a density given and I want to convert the units from one system to another or within the same system, from large to small or from small to large. Like example, let's say we have a density of a metal equal to 8,500 kilogram per meter cube. We want to convert this density to the units of microgram per millimeter cube. Okay. Now, as I mentioned before, when you want to do conversions, you need to think of conversion factors and the stages needed to convert. So here you have the numerator and the denominator. You have to convert both. So you need to convert the kilogram to microgram, the final. And you need to convert the meter cube to millimeter cube. Okay? So what you have to do next, think of the stages needed. To go from kilogram to micrograms, you need first to go from kilogram to gram, and then from gram to microgram. Okay? So now, let's think of how many zeros we have between kilogram and gram. 3, yes, 10 to the power 3. And how many zeros between a gram and microgram? 6. So what we do next, we write the ratios, but to avoid the problem of having negative powers, we compare the large to the small, or big to small, not the other way around. So which one is big, kilogram or gram? So you say 1 kilogram over 10 to the power 3 gram. This is the first conversion factor. Now here, gram, microgram, which one is big? So you say 1 big, 1 gram, 10 to the power 6 microgram. So this is the second conversion. This is the first conversion. So I need 2 conversions for the numerator. Now, to go to the denominator, I have to think of how many stages are needed here. This is meter. Think of it, meter 2. So how many stages? 1. Okay, but be careful here. You have dimensions. Here you have 3 dimensions. Just plainly, from meter to millimeters, how many zeros? 3. So this is 10 to the power 3. But because you have 3 dimensions, you raise it to the power 3. So finally, it's 10 to the power 9, the conversion. Now we write it as a ratio. Which one is large? Meter, yeah? So 1 big over 10 to the power 9 This is the conversion for the denominator. Once I have those ready, then I'll do my multiplication. So start from the number you have, 8,500 with the unit, and you always multiply, multiplication. How many factors do I have? 1, 2, so I need 3 multiplication. And remember, it's always multiplication. There's no division. So 1, 2, and this is a 3. Now, here you have kilograms, so think of the kilogram conversion, which is this. If I take it as it is, will I be able to cancel the kilogram? No, so I have to flip it. When you flip, you don't change the sign of the powers. Just you flip it, because it's 1 to 1. So this will be 1 kilogram down, 10 to the power 3 gram up. And you can see I can cancel the kilogram with the gram. So I'm in grams now. The next one is 4 grams. Useful as it is, or we flip it? Flip it. So 10 to the power 6, microgram to 1 gram. And I can see I get rid of the gram. We finished the numerator. Now we have 1 for the denominator. The meter cube is down, so I need the meter cube up. Useful as it is? Okay, leave it as it is. And then I can see the meter cube is cancelled. Now the second thing you have to do is you multiply the numbers left, numerators and denominators, and the unit left, just to check. So you have 8,500 left, no unit. 10 to the power 3 left, no unit. 10 to the power 6 unit left is microgram. Over. Here you have 1, 1, 1, 10 to the power 9.
So, Doctor, we cancel the 6 and the 8.
Sorry?
Right? The answer will be 8,500.
But I haven't finished yet. 940 millimeter cube. Now what you can see that 3 plus 6, 9. With 9, so I can cancel both with this one. What's the final answer? 8,500 microgram per. So it just happens here that if you're having the units kilogram meter cube or microgram per millimeter cube, it will be the same, as if you don't need to do all this. But of course, you have to do it to check. So this is one example of unit conversions. And just pay attention that when you have dimensions, volume, power 3, area, power 2, or just a distance or a length, power 1. Now let's take another example of conversions. Convert 3.5 years to seconds. So the question is that if 3.5 years, how many seconds you have in 3.5 years, yeah? Now I need the stages and you do it. I'll give you like 1 minute or two, just talk to each other and try to come up with a strategy. I don't need the final answer. And don't use the sheet. No. Don't use the sheet I gave you. This is a metric system. There is no help. You don't go and search for the conversion factor. You have to know it. Okay? Talk to each other. Yes?
We should just choose to do just 3 steps, or can we do more than 3 steps?
Which one? That one?
No, not that one, like in general.
It's up to you how many stages you have, as long as you get it right.
365 days, yeah?
Sorry?
In 1 year we have 365 days.
That's what I want you to talk to and check. We'll come up with the answers in a minute.
No, not 2 minutes because 3,600. Well, it's the same. It's the same. We just
Okay.
should we solve it with the answer?
What's that?
We'll solve with the answer.
Solve it if you can. You can do it quickly. You talk to. You did it?
Yeah.
But check with them. See if they get the same answer. Okay. Now, probably discussed a little bit. Now, pay attention, please. Pay attention. Leave it as it is. Stop, please. Now, one of the good way of thinking is that when you want to solve any problem, think of what might go wrong in your solution, or the way you are taking, which means look for pitfalls. Pitfalls, you have pitfalls, and when you walk, there is a pit, and you fall in it, yeah? A trap. If you avoid the traps, you're okay. You can walk straight, yeah? Without thinking of what comes next. So learn where are these traps in the question or the problem, and then you can move on easily. I call them minefields. When you walk in a minefield, what you have to avoid? The mines, yeah? Not everything. So if you know where the mines, then it's easy for you to walk. In this question, there is one mine, okay? Or probably two, 1.5 or 2. Let's do it. I'll ask this question, but be honest and just tell me what you think. Who thought of solving this by saying a year is 12 months? Raise your hand. Don't feel shy. No one? You thought that the year is 12 months. You used the conversion 1 year, 12 months, yeah? Anyone else? You used 12 months. The rest, you didn't use 12 months? Or you feel shy? Yeah? Just one? Okay, good. It's good. Okay. Now, what's the problem? This is a mine. This is a trap. If you say 1 year is 12 months, what is next? You say 1 month? You say 30 days, yeah? No, that's what you have to do. Yes? You say 30 days. Now, in a month, how many days you have? How you did it then?
I did like from years and months,
Okay.
weeks, days, hours.
Okay, so then you said 1 month, 4 weeks. A month is 4 weeks? Exactly? 28 days. Yes, 7, 7, 7, 7. So this is wrong, right, yeah? Or a month, 30 days? No, sometimes 30, sometimes 31, sometimes 28. Yeah? So going this way, give you the wrong answer. So avoid this. That's what I was talking about. Avoid the general common mistakes. Then the rest is easy. Yeah? You can drive on without any problem. Right. So which way we will go? Years to what? Days. Okay. Days to hours. There is no need 2 minutes, second. It's second. Okay. Now, years and days, what's the conversion? 300 days, yes? This is not quite right. A year is not 365 days. No. A quarter. Days. Now you might say, how come we have a quarter of a day with a year? You have either a day whole day or you don't have a quarter of a day? Okay, this is, if you calculate how long does the Earth goes around the sun in 1 year exactly, to go back to the same point, it takes exactly 365.25 of a day. So there is a quarter of a day. But of course, we cannot have a quarter of a day. Okay? We have a whole days, yeah? But in calculations, you have to include that because it's time. Now, the other thing, if you don't take this quarter of a day in consideration, what happens? Every year, you lose a quarter. In 4 years, okay? Now, in 100 years, how many quarters? 25 days, yeah? Okay. In 200 years, 50 days. 300 years, 75 days. 75 days around how many months, roughly? Which means, what happens to the calendar, which we have January, February, March, April? It will not change the calendar, but the days will shift. So like now we are in February, yeah? The weather is okay, yeah? Not very cold. But if you ignore this quarter, in 300 years, the time, at this time of the year, it won't be cold. You enter another seasons, yes? Because you shifted the calendar. So as January won't be cold at all. But January, every year, January is the coldest, yes? But if you ignore this, no, it's not cold. The season will shift with time. So to avoid this problem, you have to compensate this quarter. That's why every 4 years, February, the month of February, usually it's 28 days, yeah? Now today, what's the date today? Why today is 29 of February, not 28? Because this year is a leap year. Today is February. The date today is 29. It's a leap year. How do we know this year is a leap year? This year is 2016. Is it divisible by 4? If the answer is yes, it's a leap year. Okay? So ignoring this quarter creates a problem for people, for agriculture, when the seasons, yeah? You change the seasons, yeah?
We don't use it in other places, like in solving questions and all that.
This is theoretically, you have to take it in consideration. But of course, didn't we take this quarter in consideration or not? That's why every 4 years we add 1 day to adjust. So we don't have this problem of shifting the calendar. Okay, so this is another thing which you have to pay attention to. Now, days to hours, this is complete, yeah? Full, 24. Hours to second? 3,600. Now, write them as ratios. Which one is large? 1 year. 3,600. This is the first conversion, yeah? 1 day. Then take your number and do the conversion.
It's 11045.
Let me do it here. So, one conversion. We need 3 conversions, yeah? 2, 3. First one. And then 1 day, 24 hours, 1 hour. Right? When you use the calculator, you come up with this number. 110451600 second. Of course, when you record a number, this is not a good way of recording a number with many digits. Remember, we learned something called scientific notation. So when you have a very, very small number or very, very big number, change it using the scientific notation. So the decimal is here. Move it down. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1.1045. Okay? That's just changing it scientifically. Now we come to the subject of significant figures. How many significant figures do you have here? 9. Now, of course, this is not a practical way of writing the answers. Each time you calculate something, whatever you see on the calculator, you just record it. You have to think of how many of those are significant. Now, this is the rule here. What is the number I gave you? What was the question? 3.5. How many significance do we have here? So if this is 2 significant figures, your answer should have the same significance, not more. You cannot have an answer more accurate than the question itself. So here you have to round, yes? 1, 2, less than 5, rounding down. 1.1 times 10 to power 2 significant figures. Okay? You got the last rule I told you?
Yes.
Your final answer should take the same significant figures of the question. Okay? So this is another example of conversions. Is that okay? Yeah? Now, let's take another one. But this time, I'll show you a conversion from non-metric system to a metric system. Let's say convert 8 miles, MI, per second to kilometer per hour. Now here, miles, SI, non-metric, yes? So here you seek help from the sheet I gave you, the conversions. Of course, in quizzes exams, I'll provide you with that. So look for a conversions which takes you from the non-metric miles to the metric. What is it?
1.6.
What is what?
1 mile.
1 mile. 1.609 what? Kilometer. Okay? This is the conversions given, yeah? So what you do, you write this as a ratio. And here, you don't have to say one large, how many small. No, whatever given is your conversions. So, but just write it as a ratio. Either this one over this or this one over this, yeah? So I write it as 1 mile per 1.609 kilometer. This is my conversion. Now, this is for the mile to the kilometer. What else I need? Seconds to hours, and you know that, yeah? Hours to second, 3,600. So I have 1 hour, 3,600 second. Now we start with the number 8 mile per second. First conversion, useful or we switch them? Flip it, okay. 1.609 kilometer per 1. And I can see I'm on the right way because I can cancel the mile. What is left? The second. So flip it because second is down as well. So 3,600 second, 1 hour. Hours with hour. Sorry, not the hour. Second with second. So what is left in the top is kilometer as a unit. Bottom, hours. And multiply 8 by this one, So your answer is 46339.2. Okay? Do you accept this as an answer? No. Why not? Because how many significance you have? No, here, 2, 4, 5, 6. This is 6 significant figures. But the question, 1 significant. 1 SF. So you have to round this one to 1, yes? But before you do that, okay, 5, but you need zeros, yeah? Change it to scientific first. So this is 4.63392. 1, 2, 3, 4. And now I can truncate it out to the value I want. I need 1 significant. This one is the only one, yeah? The one after more than 5, yeah? So round up. It becomes 5 times 10 to the power 4. Right? So you should be able to convert within the same metric system, or from non-metric to metric, or from metric to non-metric. In the second case, I'll provide you with the conversion factors. But in the first case, no, you are responsible for the conversions. Now we move on to another title. Uncertainties or errors. Uncertainty or errors. What does it mean, uncertainties or errors? First of all, the word uncertainty and error means the same thing. So you can say, what's the uncertainty? Or what's the? Or find the uncertainty or find the error. I'll tell you something which you mustn't think is right. And some of you think that the word error is equivalent to the word mistake. This is wrong. Errors do not mean mistakes. You didn't do anything wrong. No mistakes. Look at the other title, or the other word, uncertainty. When you say you are there is uncertainty, mean you are uncertain, not sure, not quite sure. Not quite sure is not that you made a mistake, but there is something makes you unsure about your calculations. Yeah? So first, correct this. Errors do not mean mistakes. So what do they mean? You can think of errors or uncertainties means limitations. You are limited by something. Limitation. Now, what does that mean? Remember, in this chapter, we said measurement. You measures, yeah? So when you measure, you use tools, of course, yourself as well. Whatever you measure, there is a limitation of what you measure. You cannot be so sure about what you are measuring because of the limitation. One of the limitations comes from the measuring tool itself, the device you used. Not all the devices are so accurate. Yeah? So the errors comes from the device itself. Yeah? Limitations. So think of errors as limitations, not as mistakes. Now let's say, practical example, I want to measure the length of this room. I measured the length, and I call it L, and I found that L just for the sake of argument, is here. L is 5.74 meters. One of you measured the room length and he said this. Now, this figure, which you have here, is what you measured, yes? But are you sure that the length of this room is this exactly, 5.74? Why are you not sure? Because the measuring tape you used has limitations, yeah? What is the limitation on the normal measuring tape? Look at the figure here. 5 means 5 meters. What's this? 74 centimeters. 5 meters and 74 centimeters. On a measuring tape, what do you see? Do you see meters or not? Easy, yes? Centimeters? Easy. You see them, yes? Can you see millimeters? No. It depends. Yes or no. Now let's say the measuring tape I gave you, it has centimeters, of course. I said 74, but the ticks for the centimeters, they jump every 2 centimeters. So if you say here, this is 0, or not 0, let's say this is 2 centimeters. The next one, 4 centimeters. The next one, 6 centimeters. And you have nothing in between. Empty, no scales. So when you measured the length of the room, you found it is 74. But do you really think that it was exact on 74? Or maybe it's a little bit more, a little bit less. So a little bit more, a little bit less, you will fall in the empty space. Okay? The empty space. So that's what we call errors coming from the limitation of what you measure. So when you record the length for using this measuring tape, you have to say that I'm not sure by how much, plus or minus 2 centimeters, which means 0.02 of a meter. You are not sure by 2 centimeters, but I put it at 0.02. So it's either the length of the room is 5.76 maximum or 5.72, and all the values between these are allowed. Maximum and? Because you are not sure. It's somewhere here. It could be a little bit more, a little bit. How much a little bit more? How much? You can't, because you don't have a scale. So whatever you measure, you have a limitation. Now, if you want to have a better reading or better measurements for the length, change the measuring tape or the tool for something else. Maybe you use a laser beam. A pointer, send light, hits the wall, comes back from the time and the speed of light. It gives you an accurate length. But still, that one, how many digits will it give you? 10? Okay, still you have on the 11th, it's a limitation. Still, you cannot get it. So whatever you do, still you have some limitation, but you try to minimize the errors. So our job is that when we measure things, we try to measure to minimize the errors. Now this errors, we call it, if this is L, we call it delta L. The change in length, or uncertainty in length, or the error in length, plus and minus. And it's very important, whenever you measure things, you have to be aware of the uncertainty. Ignoring uncertainties, it creates problems in designs. I'll explain that later on, how it affects your design. Because if you ignore these small, you might think this is small, so you ignore it. But later on, when you use this figure in calculation 2, 3, 4 times, the error gets bigger and bigger, yeah? And at the end, you find that your design shifted from what is planned for. So you have to be careful of that. So this is how you record always a value plus minus the errors. This is what we call the value you measured or recorded, and this is the error. Now, if I ask you this question now, let's say I gave you this error, 0.02 meters. Do you think this error is high or low, large or small? Small. Small, yeah? Why do you think it's small?
Do we have a unit?
Because?
We have a unit, so according to
Because, sorry, I can't.
we have a unit, so according to that.
No, it's not nothing to do with. Look at the figure here. I'm sure some of you thought of this as a small because you have 0.02, yeah? A small value. Okay, now let me give you this example on the side, and then you judge. Let's say you measure something, and the value is 0.003. And there is an error plus minus of 0.001. This is the error. Is this a small or big error? But the figure itself is small, yeah? So what I want to tell you that by looking at the error itself doesn't tell you if you have a large error or small. So what you have to do? You have to compare it to the value to know if it's big or small. Yeah? So what you have to do, if you want to judge this error is high or low, compare it to the value. How? Ratio, relative. So do it as a ratio. Yeah? Create a ratio. So you say the error over the value. Now, if I take this error, I divide it by the value, 7.4, yeah? What's the ratio here? Find it for me. Use the calculator. 1 over 87. Can you see? As a ratio, it means 1 to, for everyone, 287. So what do you think? The error is high or low? Low, very low, 1 to high. But still, ratios sometimes are not clear. Like if I say 13 over 18, this ratio, you cannot judge if it's high or low or medium, yeah? We human, we are good in sensing percentages. If I say there is a percentage errors of 4%, you know, it's small. And when I say it's 50%, 60%, 70%, so it's better that you judge by taking the percentage errors, not the errors or the relative errors. This is the relative. Okay? So what we should do, we should calculate percentage errors, not errors. So stick to this, and let's find the percentage errors. So here we'll talk about percentage error. PE, percentage. How do I find percentage error? As a formula, percentage errors, I compare the error or the uncertainty to the value, but I change it to a percentage, multiply by 100%. This is the formula to calculate the percentage errors. Now let's apply it for the length, which I give you the example here. So what's the error? 0.02 over 574 multiplied by 100%. What's the percentage errors? Be careful. I've noticed that some students, they use the bottom of percentage. That will give you the wrong answer. Just multiply, divide these two, multiply by 100. Leave the percentage sign. This is 100 per 100. 0.348%. Do you agree? Do you agree? 3, 4, 3, 4, 8. Yeah, fine, it's fine. Okay, you don't have to put too many significant figures. Okay. Now, another rule, you use it whenever you calculate errors or percentage errors. Okay, record the number with one significant figures. Maybe 2 is okay, but not more than one significant. Why one significant? Because you are calculating errors. Yeah. If you calculate errors, at the end of the day, it's an error. So how come you are so sure about how many digits you have in the errors? So you record it with one significant figure. So round this one to 1. 0.3%. Is this high or low now? It's easier for you, yes? It's even less than 1%. When we change it to percentage errors, it's clearer. So learn to find percentage errors. Now, in a percentage errors, how many variables do I have? Look at the equation. How many I have? 1, 2, 3. Now, what we did here, we worked on this side, yeah? And this was the unknown. Now, you have to learn to look both ways. Equation means that you have to be able to work this side or this way or this way. Most of the time, you work from left to right. Okay? Now, let's do this in an example. So write this example with me. The mass of an object is 10 grams, and there is an uncertainty of let me correct it. There is a percentage uncertainty of 4%. What is the error in the mass value? So we have the mass of an object is 10 grams, and there is a percentage uncertainty of 4%. What is the error in the mass value? Okay? This is your equation, yeah? What is given? What is given? Percentage errors and? What is unknown? So put here X, the unknown. So PE %, X 10. Okay. Now, of course, it looks like it's a simple question, but there are some things. Sometimes students get things wrong in calculating using the calculator. Can you see the percentage here? Don't ignore it. This is 4%. No, you don't have to. Look here, you have percentage here and percentage here, yeah? They cancel each other. So what is left? 4 multiplied by 10 over 100 equal X. So X is plus minus 0.4 gram because it's an error, plus minus. Okay? So be careful of this percentage. Right. Now, I'll give you two rules how to handle calculations, numbers, yeah? Because we need them. Like what we learned in significant figures. But here, two rules which you have to follow when you do calculations. In mathematics, how many operations we have? 4. Addition, subtraction, multiplication, and division. Okay. The first rule is about multiplications and division. The second one, subtraction and addition. Rule number 1. I'll write it down and then we discuss it. So just write with me to save the time. When it's part of the subject in the whole. When multiplying or dividing several quantities the number of significant figures and the final answer should be recorded. Least when I write things quickly, I get them spelling wrong. Right, I read it for you. Rule number 1. When multiplying or dividing several quantities, the number of significant figures in the final answer, the final figure, should be recorded with the lowest number of significant figures in the question itself. Got it? You finished writing? Okay, now, what does that mean? Let's take an example of multiplication. Let's say I have two numbers. 3.25 multiplied by 5.789. Here I'm multiplying two numbers, yeah? Of course, you'll use the calculator. Now, you use the calculator will give you this figure. 18.81425. All right? Now, what does this rule say? It says when you multiply numbers or divide numbers, your final answer should take the least number of significant figures in the question itself. How many significant figures do I have here? 3 significant figures. Here? 4 significant figures. At the moment, the answer, how many does it have? 7. Is this allowed? No. Why is not allowed? Because you're saying that I have an answer more accurate than the question itself. The accuracy has 3, 4, and you say 7. So what you should do? You take the least here. What's the least? 3. So you round this one to 3 significant figures. So it means 1, 2, 3, and you round the 1 down. So your answer, 18.8. 8, and this will be 3 significant figures, and this is the least, similar to this least in the question. Okay? This is the rule. Of course, use this rule in this chapter. Later on, we don't abide by this rule a lot because we don't want to stop in every step and calculate how many significant. But this is the general rule. You have to know how to use it. Yeah? Scientifically, this is how it should be. The second rule, this works for division and multiplication.
So this is for every operation we do in the question, if it has like many operations?
It's better to not, if you do it in every step, which means in every step you're doing rounding, and then at the end of the day, your answer will be far away from the real answer.
So the last one.
Okay, so that's what I said. Use this rule in this chapter as a practice. But later on, no. It's not like in every step you calculate how many. I'll tell you the rule which we use here. In the chapter 2, 3, 4, always work with the 3 significant figures. Not more, not less. So you don't lose the accuracy and you don't put too many digits. But this is when we are in chapter 2 onward, yeah?
You will not do like the multiply by 10 by 2.
Oh, you want to change it to, it's up to you. You want to change it scientifically, no problem. But this is not a big number, 18, to change it to a scientific notation.
4 to 5 group.
No, this is a big number or a small number. So you don't need to write it as a scientific notation, 10 to power. Just do rounding, 7 to 3. The second rule, write quickly with me. But the second one is about addition and subtraction. So when adding or subtracting numbers, the final answer should be recorded with the least, this time, least decimal places, not significant figures, with the least number of decimal places in the question. So in addition and subtractions, what's the rule? Take the least number of decimal places, not the significant figures. Example. Let's say you have 2.45 plus or minus, it doesn't matter, 1.2 equal. Now if I add it just normally, what's the answer? 3.65. Okay? Now, the rule is not about significant figures. It's about decimal places, addition and subtraction. Here, how many do we have? No, significant figures. Decimal places, sorry. 2 dp, decimal places, 2. Here, 1 decimal place. Here, how many I have? 2 decimal places. So what's the least? So you have to round this one to 3.7. Here, I'll have 1 decimal place, least, similar to the least in the question. Okay? So take the least number of decimal place. Right. Now we come to the rich topic. It's about errors, but how do you apply errors? This is, by the way, it's not in the textbook. This part is not in the textbook, but because you need it, and you need it in the physics lab, I cover it usually, errors and uncertainty. They cover it in the lab as well, but maybe this will help you before you start the lab. Okay, so the title is now Propagations of Errors. Propagation of propagations of error. We talked about errors. Huh? We said whatever you measure, there's an error. That's when you have one value and you have an error in it. But imagine or suppose that you have many variables, 2, 3, 4, and you come up with values for each. And each one of them has an error. When you plug in these values in a formula, what happens? You are accumulating the errors, and errors from length, error from width, error from mass, error from time. In a formula, you'll end up with an error in the final answer. How do you calculate the final errors? This is what we call propagations of error. The word propagation, similar to the word, if you have fires, like if you have a small fire here, that's an error, yeah? A small fire here, a small one there, small one there. These are small fires, yeah? Now, when they combine, you'll have a big fire. The word propagation is like propagations of fire as well. The fire sneaks slowly, small, and suddenly becomes a very large one, yeah? So errors like that, they propagate through your calculation. Before you realize that you have that much, it will be too late. You have a big error in your design, in your calculations, because you didn't pay attention to the propagations of errors. So let's start with an example. Okay, but before I give you the example, there are three methods to calculate the propagations of errors, yeah? 3 methods. First method, I don't use it in this course, but you should be aware of it, by finding the maximum and minimum. I'll explain that in a minute. Maximum and minimum. And finding the propagations of error. The second method, by using calculus, derivatives, calculations. And this is the method we use in this course. And the third method is more accurate than the second method, but we don't use it. But just in case you do a search on the net and you find this method, you don't know what's about, so at least you have an idea. But we don't use it. It's the diagonal method, using the right angle triangle. So we stick to the second method. So let's say I'll start with the example, it's better. Let's say I have this room. I want to find the area of the floor of this room. So what do you need to measure? Length and width, okay? So, and the question is, what's the area? Now, if I say what's the area, it means area without taking in consideration the errors. And the second part is, what's the uncertainty or the errors in the area calculation? How much errors you have in the calculations of the area. So write the example with me, and we'll discuss it. Find the area and the uncertainty in area of a rectangle. The shape is a rectangle of length L. You measure the length, it's 3.25, but there is an error plus minus 0.01 meter. And you measure the width, W, 1.76 plus minus 0.02 meter. Find the area and the uncertainty in the area. Two parts. Now, before we answer that, let's look at the errors here. How much errors do I have in the length? 0.01 meter. Okay? So it means how many centimeters? So this is a plus minus 1 centimeter. Here. Now, why here I have 1, here 2? What does that mean? It means that when you measure the area, the length and width, you didn't use the same tool. When you measure the length, you had a measuring tape with an error of 1 centimeter, which means it shows 0, 1, 2, 3, 4, 5 centimeters, yeah? But the second one, 0, 2, 4, 6, 8, yeah? Possible, you change the tool. So that's why you have differences in the uncertainty. Now, the first part, I think is easy. What's the area? How you find the area of a rectangle? What's the formula? Area equal length multiplied by width. So let's multiply this one. You have 3.25 times 1.76, and this is equal to 5.72 squared meter. Now let's apply the rule. Rule number 1. How many significant?
3.
So the least, yeah? You don't have to do rounding. But don't be fussy, as I said, just in this chapter. Later on, don't. It's not like every step you check. So this is the first part, the area. Now the second part. What's the uncertainty in the area? What does that mean, uncertainty? Remember, uncertainty means errors, yeah? So errors, what means? Here you have A plus minus delta A. This is the uncertainty or error. I want delta A. Now if I ask you this question, and tell me what comes into your head if you want to calculate the errors in the area, what you should do? Wait. Multiply the errors. She said multiply the errors. I'm repeating the question because there's no recording for the student. Okay? She said the question, the answer from her, she said, I'll multiply this error by this error. Now, if we ask her why, she says probably because here you have multiplication. This, okay? You subtract these. So she's saying that I'll subtract them. Why? But this delta, okay, she said, because we want delta, and delta is subtraction, yeah? But this is subtractions of areas, not subtractions of length and width. So this is the wrong conclusion, yeah? This, if you subtract these, you're subtracting length from width or width from length. This is not area or errors in area. Okay? Any more?
Is it like A2 minus A1?
A2? Okay, she's saying I find A2 minus A1. What is A2? What is A1?
Like we plus and minus the error?
That's, she's saying I take L first plus, so it means maximum L, W plus maximum. So when you multiply maximum L, maximum W, you get maximum A. Then minimum L, minimum A, it gives you minimum area. So you have maximum area, minimum area, yeah? And then you subtract. This is the first method I told you about, which we don't use, okay? This is when you're stuck and you look for a closest exit. You do it this way. But again, even this one is not an easy one because here it's easy. Because you look for the maximum area and minimum area. But what if your equation is not as simple as this? You have plus, minus. How you maximize the value? How you minimize? It's not like taking the maximum, all the minimum. It doesn't work like that. Like if you have equation x plus y minus h equal z. What's the maximum value of z? Will you take maximum x, maximum y, and maximum h to get maximum z? Wrong, because this is minus. So you have to do the opposite here, yeah? You have to take the minimum h with the maximums of x and y. So you have to be careful. It doesn't work as simple as she said, yeah? But if you are sure to find the maximum value of the function and the minimum value of the function, then subtract, you get the difference between maximum area and minimum area. And then you divide it by 2, the difference by 2, then you get the errors. Because you have A max, A min, subtract them, you get this, and then divide it by 2, you get the central, yeah? And from here to there is the errors, plus or here the minus. So you need to divide by 2, the difference. So the maximum, minimum, minus over 2. So this is one of the methods. Now, the second method, remember I said, is by derivatives, yeah? We use what we learned in Calculus 1, derivations. One of the meanings of derivations is errors. When you say dy over dx, this is derivative, yeah? Let's say dy over dx is equal to x, yeah? Can I separate dy from dx or not? So I'll have dy. What does it mean, d? The other meaning is delta, but small. D equivalent to delta. But d is very, very small. Delta is a difference which is big, not small. So when you say dy, what do you mean? The errors in y. When you say dx, the errors in x. So that's why one of the meanings of derivatives is errors. And we use this idea to apply it and find the errors there. So what are the steps to find the uncertainty here in the area? Now, generally speaking, not this question. Whenever you want to find the propagations of errors, first thing, you have to have a formula to use, yes? In this question, do we have a formula? The area, number one. Number two, to find the propagations of error, you take the formula and you derive it. Find the derivative. But it's not xy. Think of all the variables as y, dependent. There is no independent. It's not like x and then y. No, x is like y is y. Z is like y. Treat them like y as the main function, which means you are separating the variables. I'll explain that in a minute. You might not get it. But just treat them separately as individual entities. So take the formula, derive it. The derivations of the formula is the errors. Okay? So now if I take this equation, A equal L by W. This is my formula. I start with it. I do the derivatives separately for the left and for the right. If I have A, area, what's the derivation of A? dA. Okay? Done. Equal. Now this side, I have two variables, L and what's the operation? So you have to use the rule of multiplications in derivatives. So how you do that? First, multiply by the derivative of the second, plus the second, multiply by the derivative of the first. So first is length, dW. By the way, don't use a prime here. Prime is in calculus. Here we don't need a prime, we need D. Errors. dW plus dL. What do you see here? Now read, not using mathematics, using physics. Errors in A equal value of the length multiplied by the errors in the plus width, errors in length. Substitute now what you have, you get the errors in area. So dA equal 3.25 multiplied by 0.02 plus 1.76 multiplied by 0.01. And this will give you the uncertainty in the area. And you'll find that the answer here is plus minus 0.0826. Now, follow the rule. How many significance we have here? 3. But here, it's a mix of multiplication and addition, yes? But don't forget, I'm calculating errors. For errors, don't use the rules I gave you. Just use the general rule. One significant figure, regardless of what you do. Errors, just record them with one significant figure. So round this one to one significant, 0.08. Plus and minus. This is the error area. So now the final answer is 5.72 plus minus 0.8 square meter. This is the area and the uncertainty in the area. Okay? This one?
Yeah.
This is dW.
Yeah.
This is dW, arrows in width. And this is arrows in length, dl.
يعني الإيرورز ونفسها ال
Sorry?
الإيرورز
Plus minus. When you say plus minus, it means this, the arrows. This is the value.
يعني الإيرور هو نفسه اشتقاق.
No, these are the numbers.
Yeah, but
You are deriving the formula.
when you're deriving the dW,
No, I'm not. What does it mean, dW? The errors. It's not you derive something. dW, the meaning of dW means the errors in W. The errors in W. It's not like you derive something again. Another example. This time we take a question of physics. The distance moved by an object is 4 plus minus 0.1 meter. And the time taken is 2 plus minus 0.2 seconds. Find the average speed and the uncertainty and the average speed. The distance moved by an object is 4 plus minus 0.1 meters. That's the distance moved with an arrow. And the time taken is 2 plus minus 0.2 seconds. Find the average speed and the uncertainty. Remember, I use the word uncertainty sometimes error. So I want you to get used to using both. It means the same thing. Right. First part comes to the definition of, remember, to find uncertainties, you need propagations, you need a formula, yeah? Here we are talking about average speed, so we need the formula for average speed. I'll call it S average, AV. How do you find average speed? By dividing the distance over time. Now, during the course, I'll use D for distance. But here I'll avoid D Because D, I use it for the sign of derivatives. So be careful, yeah? I'll put X over T. Okay. Now, what's the average speed?
4/2.
4/2, which is 2 meter per. This is the first part. Now we go to the second part. What's the error in S? Remember, to find the errors, you need a formula. Do we have a formula? What is next? The derivative of the formula. And then we think of what is the uncertainty. So the derivatives of the first side, let's say S equal X over T, S average, ds. Now here, what do I have? Division, yeah? So what's the formula? T square, T. Wrong if you say T, it's okay, you can swap them. T dx. Dx, yes? Now, I have a reason why I put T first. Because some of you make this mistake. They put X dt here. Now, whatever you have here is the first one. T, T, X, X, and the second derivative. So T dx, you say minus what? X. Okay? This is in calculus. Now, here we have a slight change. This is the formula in calculus, how you derive, yes? When you use derivations for errors, you change the minus to plus. The minus here, change it to plus. So, plus, and here, write a note. What we did, we changed the minus to plus. Of course, you'll ask why, yeah? Why? Imagine it's minus, not a plus. Okay? And let's say you multiply T by dx, and the answer is, not this question, general. The answer was 3 for T multiplied by dx. And when you multiplied x by dt, it was a 3 as well. So what you'll have, 3 minus 3 over whatever, yes? T squared. What's the answer?
0.
Which means that there is no errors in the average speed. Is that possible? You have errors in the distance, and you have errors in the time. When you combine them, there is no error. There is no such a thing you can cancel the errors. So to avoid this problem, you have to change the minus to plus. Got it? So there is no minus. You change it to plus. Now apply it now. What is T? 2. dx plus x dt over 2 square, and you get the answer for the uncertainty, 0.25 plus minus unit meter per second. How many significant? 2. But this is an error. Rounded to 1. 0.3 meter per second plus minus. 1 significant figure. Now I'll speed up a little bit because we have 5 minutes left. Same idea, propagations of errors, yeah? So what we learned from this, if you want to do propagations of errors to find the final, you have to have a formula and derivatives of the formula, yeah? So always, most of the time, you are responsible for this formula. You have to discover what formula you need. And it's not difficult because I'll ask you about formulas which you already know. Okay. Now, let's say I'm talking about this formula. No, not always, not always. If there is a formula which you must know, basic, you have to It's not like I provide you with everything. Like, let's say this room. Does it have volume or not? What's the shape of the room? How? It's a no. A cube means the sides are equal, yeah. But this is not equal. It's a box, yeah. So what? How do you find the volume of this room? Volume of a box. So this is the formula we're talking about. You have to know it. It's not like I give you a formula: length, width, and height. I say a box. You say length, width, height. Okay. Now what I'll give you? I give you the length and uncertainty of length. Width, uncertainty of width. H, uncertainty of H. I say, what's the uncertainty in the volume? What you have to do? Derive. Now, how you derive this one?
One of them will be constant.
If you don't know, go back to your calculus. You know how to derive 2, like the one area, yeah? But when it's 3, 4, 5, some of you have problems, yeah? So how you do that? Take 2 of them and call it something else. Let's say I call Z is WH. Okay? So what is my question is now V equal L multiplied by Z. What's the derivatives of V? L dz plus Z. Okay. I can put Z back or not? But I need dz, derivatives of Z. So derive this. What is dz? W dh plus h dw. You substitute this one here. So L W dh plus h dw plus the Z is WH dl. When you open the brackets, you'll have L W dh plus LH dw plus WH dl. Now, you may think this is that hard to remember. Difficult? No. There is a pattern here. Look at the pattern here. How many we have? 3, yes? How many terms? 3. Look at the first term. You don't touch L, you don't touch W, but what you do? You derive one of them, H. So leave LW, derive H, plus leave other 2 and derive the third, W. Leave another 2 and do it. So if you have 4, fix 3, derive 1. Fix another 3, derive 1. Fix another 3, and you have 4 terms. If you have 50 terms, 50 variables, you'll have 50 terms. So fix 49, derive 1. Fix another 49, derive 1, but you'll have 50 terms. So this is how you do it. Now, another one. The architects, they use shapes, yeah? Which means you are good in knowing shapes. And you can't say, I can't remember the formula for this shape, like the box. Now, what's the formula for the cube? If you have a cube. L cube, V, L cube. This is a cube. So what's the uncertainty in the volume of a cube? What is dV? 3L square dl. You must have d in every derivative, yeah? Now you have a sphere, a ball, with a radius r. So if you have r and uncertainty in r plus minus delta r, what happens to the volume? You have uncertainty in the volume. How do you find the uncertainty in the volume of a sphere? You need the formula for the sphere. What's the volume of a sphere? Yes? What's the volume? I don't know. You're not going to design a ball, on top of it a salad. Okay? You have to know you Google. There's no electricity in the day.
We don't need the volume.
I don't need the volume. No, you need the volume. Because in density, you need mass over volume. So you need the volume. So what's the formula for the volume? 4R? No. 4 over 3 pi r cube. Now, what's the derivative here? What is dv? 4 over 3 pi. This is constant numbers, yeah? Derive the r cube. 3r square dr. Don't forget the dr. dr means the arrows in the radius. A triangle. This is H and this is B. What's the area of a triangle? Half base height. So what's the uncertainty in the area? dA. Where is the mistake you'll do here? This half. This half multiplied by the derivative. So half, open a bracket. First derivatives of the second plus the second derivative of the first. And then the half will be multiplied by both. More? Yes. One more. A triangle as well. But this time a right angle triangle. This is theta, 90. This is x, this is y, this is z. Now think of the formulas which you can give me about a right angle triangle. What is the first formula? X square plus y square equal z square. Good. What else? Sine theta equal y over z. Cosine theta, tan theta. Now this is the question here. If you have arrows in x and arrows in, what's the arrow in the z, in the hypotenuse?
Equal x squared plus.
What is your formula? First one. Because it has z, x, and so what you have to do? Derive it. What's the derivative here? 2z dz. 2x dx plus. Okay, where is the answer? I want dz only. So dz, 2z, 2x dx plus dy. This is the uncertainty in the hypotenuse. Of course, you can find the uncertainty in the angle theta by using, but you have to know or remember derivatives of trigonometric functions, sine, cosine, tan, yeah? Okay? Hi. You remember we started in the previous lesson talking about arrows and percentage arrows and the methods to find the percentage arrows and the propagations of errors when we have more than one source of errors. There's one part which is left, and we complete that subject, and then we move on to chapter 2 today. Okay? So the part which I'll cover today is about how to calculate the propagations of errors if you have a trigonometric function, like sine, cosine, tan. Yeah? So if your function is a trigonometric, how do you find the propagations of errors, or errors in general? Now, suppose my function is z equal sine x. Okay? This is my function. And the x has a value, which is the angle here. Let's say that x is 30 degrees, but there is an error of plus minus 1 degree in your calculation. So this is x, and this is what? Delta x, errors. And this is the value. Okay? Now, the question is, what is the errors, or what's the uncertainty in the sine x, not x. X is 30 plus minus 1. So how do you find the uncertainty in the function sine x, which is z? The question here is find dz. The errors in z. Or the uncertainty in z. So what we do usually, we said, derive the function we have, yeah? So let's derive this function. Z equals sine x. What's the derivation of z? dz. Cosine x dx. Remember? You must have it. Now, this doesn't mean dx multiplied by x. dx multiplied by cosine x. Number one. Number two, this x, you cannot do anything about it because it's bound by a cosine. So you cannot multiply anything or take something out. This is the angle. Now, I have to evaluate, yes? How much is x? So now, cosine 30 degrees, yeah? Okay. What I need now? dx, which is the error, yeah? Delta x. How much is the error? Okay. Here you have to be careful. 1 degree, yes? What we did here, we used calculus, yeah? Derivatives. Calculus, derivatives, especially sine, cosine. Why the, like, what's the derivative of sine? You said cosine, yes? And what's the derivative of cosine is minus? But why is that? Based on what? If you go back to calculus 1, you'll find that sine x is equal to cosine x derivative by using the limits definition, yeah? Through that, you based your calculation on the assumption that limit sine x over x when x approaches 0 is equal to 1, yeah? You use this formula to prove that sine x derivative is cosine x. It means x, when x approaches 0, the limit, sine x is equal to x as well, yeah? Because this is by 1. Now, this formula is true. There are two conditions for this. This is not always true. This formula is true when x is what? Small, because x approaches 0, it means x is small. The other condition, which I don't know if you remember, this formula is valid when x measured in radian, not in degree. You cannot say sine 30 over 30, like the angles in degree, or sine 1 degree over 1 degree, if you take x very small, yeah, is equal to 1. It's wrong, yeah? So what's the condition for this one? X is small, approaches 0, very small, and x measured in radian. So when you do derivatives here, of course, if you say sine 30 in degree, or you say sine 30 in radian, the answer is the same. Like if you use the calculator, what is sine 30? Or it's 0 root of 3 over 2, or you can write it as a decimal, yeah? Okay, now this is if you use degree. But what is the cosine of 30 in radian? Will it give you a different value? No. Yeah? So change the 30 to radian and say cosine the 30 in radian, it gives you the same value. So we don't have a problem with the cosine and sine. Yeah? You can use degrees or radian, the answer will be the same. But the problem lies where? In the dx. This is not sine or cosine, yes? This is the change, the errors in x. Remember, x is measured in, but this is measured in, so it's not possible. You have to convert it. So whenever you have dx, you have to multiply it by the conversion factor, pi over 180 degree, to change it from degrees to radian. So be careful of this. Okay, so now the answer is pi over 180. And pi here is 314. Now you can multiply, and it gives you the dz, plus minus. Okay, one of you give me the answer, so I can put the final answer. This is 314, root of 3. The answer is 0, 0, another 0, 4, 1, 5. Okay, plus minus this value. Yeah? Remember, we said errors, we usually report them with one significant figure. So round this one to 0.02, because 5. So the errors in sine x function, yeah? Now you can try now cosine, yeah? Tan, any function. But what you have to remember, the d must be measured in, so convert it, because the conversion says a pi rad in radian is equivalent to 180 degree. So this is the conversion factor. Either you say pi over 180, remember, or 180 over pi. This is rad, this is degree, here, this is rad, degree. You switch it the way you like if you want to convert. So if you are converting from degree to rad, degree will be here, yes? Rad, so this is the way you do it. But if you have rad, you have to use this one, because rad with rad cancels, it becomes degree. All right, so this is very important in trigonometry. Now, let me give you one more of trigonometric. No, this is the arrows, yeah. Yeah. This is the dz. No, sine has no units. Your function is sine. So for a sine, you don't have units. It's just a number, yeah? Plus minus now.